6.1, electromagnetic induction. First, did we define first what does EMF mean? Yes. EMF means any device which produces electrical energy. It's called source of electromotive force, yani EMF source. There are two types of EMF sources. One of them is chemical batteries. Everybody knows about this in our life. So like we're going to put inside a remote control device or inside a toy, these batteries. But these batteries provide EMF by chemical reactions, electrochemistry. You are going to study this. Did you start studying? No. Chapters? 8. But second method is electromagnetic induction, which is our way. Chemical batteries are practical, yes, you can carry it everywhere, but they are not powerful. That's why this method is saving your life. Yani our life is completely dependent on electromagnetic induction. So definition of electromagnetic induction: inducing means producing. We are not going to use producing. I have a special term for electromagnetic induction. Inducing electric current by using magnetic field is called electromagnetic induction. And there are two methods of electromagnetic induction. One of them is pulling a conductor perpendicular to magnetic field so that it crosses magnetic field. These are keywords. When we pull a conductor perpendicular to a magnetic field, say that this is the conductor. So like this, magnetic field is cross, which is into the board. I'm going to pull this conductor from left to right like that. When I was pulling this conductor, because there are mobile electrons, valence electrons in a conductor, I am at the same time pulling these mobile electrons to the right. As I am pulling them to the right, I will find out that a magnetic force acts on this electron. Because if a charge is moved inside a magnetic field perpendicularly, a magnetic force acts on this charge. We calculate this magnetic force as 5.3, 2 times V times B. So, and this is going to be magnetic force acting on the electron. Magnetic field is cross, which is into the bench. We are pulling the conductor to the right. So back on my hand is the force acting on electrons. And all these free electrons, mobile electrons, are forced to move down to the bench. So then they will accumulate in the lower end of the conductor. When they accumulate at the lower end, of course they leave upper end. So upper end becomes positive and lower end becomes negative. Is it just like a battery? A battery is a positive and negative terminal? Yes, it is. Yeah, if you pull out a conductor perpendicularly in a magnetic field so that it crosses the magnetic field lines, so you can calculate an EMF. You can measure an EMF between the ends of this conductor. And this EMF can be calculated by an equation. Absolutely magnetic field. Without magnetic field, no magnetic force. And everything related to the magnetic force is going to be related to this EMF. So magnetic force acting on a charge depends on B, magnetic field intensity. EMF depends on B. The force acting on the charge inside magnetic field depends on velocity. So also depends on your direction, in which how fast you are pulling it, yani V. Also depends on how many electrons are there, which is the length. L, yes, it's in L. BLV, yani believe, is the equation for calculating induced EMF when you pull a conductor inside a magnetic field perpendicularly. But if you don't pull it perpendicularly, what happens? Depends on how you pull it. If you move the conductor parallel to the magnetic field, which is the quiz question, so no magnetic force acts on the electrons, and no magnetic force acts on the electrons, so there will be no polarization. Why should the electron move in this case? So there will be no positive, no negative, no induced EMF. But if you pull the conductor not parallel, inclined, any angle, or perpendicular, in this case, there will be an EMF. Because the conductor is crossing magnetic field line, it was the keyword. When you are pulling a conductor, it should cross magnetic field lines. You can make it crossing perpendicularly or making an angle include, but not parallel. Okay, believe me. So that this EMF depends on magnetic field intensity, length of the conductor, and velocity, yani your direction of pull, magnitude of the velocity of your pull. This terminal is positive, this is negative. We said that this conductor is polarized. Upper end is positive, negative, lower end is negatively polarized. But if we change direction of the pull, this happens different. Look at that. So this was the one which we are pulling to the right. So according to the right hand rule, upper side is positive, lower side is negative. But if we change direction of the pull, look at what happens. Upper side is negative, lower side is positive. Yani polarization becomes opposite if you change direction of the pull. Not only this, change direction of the pull, this one from cross magnetic field cross to the dot. Yeah, nothing else is going to be changed. Make it dot. If magnetic field is dot, which is out of the page, now direction of the pull is to the left. Magnetic field is out of the page. Look at that. If I go like this. So upper side is palm is positive, back is lower side is negative. And magnetic field comes out. We are pulling to the left. So upper side is positive, lower side is negative. Then we can say that two things can change polarization of the conductor. One of them is direction of the pull. If you reverse direction of the pull, so magnetic force acting on the electron becomes opposite, that's why polarization becomes opposite. And second one is change direction of the magnetic field. If direction of the magnetic field becomes opposite, again, magnetic force acting on the electron becomes opposite, and polarization changes from negative to positive, positive to negative. Malzemenizdeki de biraz farklı, ona takılma fazla, tamam mı? It's a bit different. I put all of them on one slide, okay? And also, in your malzeme, I said them do something. There was a mistake, so it changed, okay? And this is one method. Put a conductor inside a magnetic field so that the conductor crosses the magnetic field lines, one of them is this. But this method is not very effective. There's one more method. And all the chapter 6 know about this method, the incoming one. Induce electromotive force in a loop or loops by changing magnetic flux through the loop. We can change the magnetic flux by three ways. One of them is we can make a change in magnetic field intensity. We can make changes area perpendicular to the magnetic field, or we can change the angle, theta, orientation of the loop. Now we are going to study them one by one. First, by changing magnetic field strength through the loop. Okay, so this, look at that. This is a bar magnet. Bar magnet, this magnetic field around is not uniform, non-uniform magnetic field. And we are moving this loop from a low far position to a close position, as we see. As we are moving from far position to close position, what happens to the magnetic flux? Increase, because in here magnetic flux is weak, magnetic field is weak. When a close position, magnetic field is strong, close to the poles. So magnetic flux directly proportional to magnetic field intensity. Move a bar magnet and a coil relative to each other. Yani make coil approaching the bar magnet, or make bar magnet approaching the coil, or make both of them approaching and moving away from each other. But while we are doing that, be careful about one thing. It is keep this loop parallel to magnetic field lines. Why we should not do that? Polarity loops must not be parallel to magnetic field lines, because if it becomes parallel to magnetic field lines, now look at what happens. Outside, look at outside, then you are going to pull it inside. Outside, magnetic flux through the loop is zero. Initial magnetic flux is zero. Then pull it inside, from outside to inside. As you are pulling from outside to inside, what happens? Magnetic flux is still zero because lines are parallel to the loop. If the magnetic field lines are parallel to the loop, magnetic flux is zero. So is there a change in magnetic flux? So, if no change in magnetic flux, no induced EMF. That's why while we are moving look from outside to inside of a magnetic field, or from inside magnetic field to outside, you shouldn't pull it parallel to magnetic field lines. You can make any angle different than inclined possible, perpendicular to best. The most change in magnetic flux happens if you pull it outside perpendicularly. So this is the first method. Second one is change the area. Now by the time, we can also move before that, we can also move this loop inside a non-uniform magnetic field perpendicular like this. Look at that. This is a region of non-uniform magnetic field. How do you understand that? Separation between the dots are changing from left to right. Separation between the dots tells you that weaker magnetic field. In here, stronger magnetic field right there. As you're pulling this loop perpendicular to magnetic field lines, magnetic flux is changing from big magnetic flux to small magnetic flux. So then if magnetic flux changes, so we expect there to be an induced current and induced EMF. One of the business. Second one is area. We can change the area. Effective area of the loop. What is effective area? Area perpendicular to magnetic field is effective area. So this is the region of uniform magnetic field this time. Separation between the dot side, same. So when I was taking a look from outside to inside, what's happening? Effective area. Area perpendicular to magnetic field initially zero. No magnetic flux in here. Later, when you take it inside, what happens? Increases area, effective area increases, magnetic flux increases. So, is there a change in magnetic flux? So then there will be a current, induced current in the loop. But as this loop is moving inside a magnetic field, or uniform magnetic field, so everywhere the same intensity of the magnetic field, same magnetic flux, no change in magnetic flux, no induced current, no induced EMF. But while we are taking the loop out, effective area is this time decreasing. So magnetic flux is also decreasing. So then, if there's a change in magnetic flux, we can induce. And if it's a uniform magnetic field, the induced current or induced EMF happens while we are taking a loop from outside to inside, or inside to outside, but perpendicularly, or at least inclined, not parallel. There's one more method about inducing an EMF by changing the effective area. This is one of the chapter 2 question. Stretch a loop inside a magnetic field. Look at that. Initially the loop is circle. Effective area is very large. When you stretch it, effective area decreases. So magnetic flux also. So we expect an induced EMF, induced current, in this case as well. This is related to one of the chapter 2 question. And third method is theta. We are going to change angle, theta. Yani rotate a loop inside a magnetic field. So as now rotating a loop inside a magnetic field, when the loop is parallel to magnetic field lines, magnetic flux is zero. Then as you are continuing rotating, magnetic flux increases and becomes maximum. Then decrease and becomes zero, or increase and become maximum. This is the best method. That's why the section 2 was complete about that. It is the method of AC generators. Rotate a loop or loops or coils inside a magnetic field. As you are rotating them inside a magnetic field continuously, of course, magnetic flux continuously changes, and we get a continuous EMF from this loop or coil. Okay, now we are going to define induced magnetic fields. And we learned that to induce a current or EMF in a coil, we have to move a bar magnet closer or away from the coil. So as we make them closer or away, magnetic flux to the coil is changing. And this changing magnetic flux induces a current on the coil and also EMF. And normally, this is a permanent magnet. Its magnetic field always exists. One magnetic field, but this is a coil. When this coil has a magnetic field, if there's an electric current. So if we keep them like this, only one magnetic field exists, which is the magnetic field of the bar magnet. But if we move them closer to each other like this, because magnetic flux through the coil is changing, this coil also induces a second electric field, electric current. And this electric current on the coil, which is induced electric current, produces another magnetic field. And then when we move them closer and farther to each other, two magnetic fields exist now. One of them is the applied magnetic field of the bar magnet. Second one is the magnetic field of the coil, which is magnetic field of the induced current. And magnetic field of this induced current is called as induced magnetic field. Now we are going to talk about this induced magnetic field. So assume a bar magnet is being pushed. Now we are going to push it into a coil of wire or a solenoid or a loop. When we do that, we are going to observe that in this coil a current is induced. This bar magnet has its own magnetic field, we named as external magnetic field, or sometimes we named as this applied magnetic field, but this current has its own magnetic field too. This magnetic field is called induced magnetic field. When we move them closer or farther from each other, there are two magnetic fields. One of them is the magnet's magnetic field, second one is the induced current's magnetic field in the coil. And we also learned in chapter 5, section 2, if there are two magnetic fields, they interact one another. They can attract or repel each other like two magnets have two magnetic fields. So now we are going to discuss about this. At which cases these two magnetic fields try to repel each other, at which cases they tend to attract each other. Now we are going to define this. If a coil and a bar magnet are made approaching, yani when I am pushing this bar magnet towards this coil, made approaching. So a pair of force that tends to repel each other is created between the coil and the bar magnet. Yani, even though I am pushing this bar magnet towards this coil doesn't want this bar magnet approach itself. That's why this coil tends to repel this bar magnet. And they tend to repel each other when I was making them approaching each other. So this is the case. Here is the coil. Here is the bar magnet. We are making them approaching, we understand by looking at the direction of the velocity. As you see, this bar magnet is approaching to the coil. So then we are going to decide which end of this coil is M pole, which one is S pole, by checking which end is approaching. So this is a bar magnet. Every bar magnet has a specific M pole and S pole. Look at that. According to this given picture, this M pole is approaching. And the approaching one is the M pole. If M pole is approaching, so if they should repel each other, what should happen? This pole must be N, because we know that N and N repel each other. If this pole, this side is M pole, that side is going to be S pole. But if we push this bar magnet towards the coil, so S pole is approaching, this time they will tend to repel each other, because S is tend to repel by another S. This must be S, this is going to be. Then we said that in the case of approaching, you make a bar magnet approaching a coil, or a coil is approaching the bar magnet, or both are approaching to each other, and if they relatively approach, unlike poles face each other, because like poles tend each other, because like poles tend to repel each other. N and M face each other, S and S face each other. And also, we can decide this in terms of the magnetic field, because if two magnetic fields are opposite in direction, they will tend to repel each other. Look at that. We know magnetic field lines are leaving from M pole. Look at the magnetic field of this coil in this case. It's to the right. Look at the magnetic field of the bar magnet here, to the left. Are they opposite in direction? They are opposite. One of them is to the right, and one is to the left. So opposite magnetic field tend to repel each other. And here, look at that. Bar magnet's magnetic field is to the right. For coil's magnetic field, it's entering the S pole. You know, magnetic field always enters S pole. So this magnetic field is to the left, but that one is to the right, they are still in opposite direction. They again tend to repel each other. We can also go by this way. So this is the one-on-one. If you make them approaching, they tend to repel each other, like poles must face each other. Second case, what if we make them moving away? If we make them moving away, of course I am going to do that. If a bar magnet is moved away, passive voice I am using because we are moving them away. They don't want to move. We take them away. That recedes. If I pull this bar magnet from this coil, like this is the case, here is the coil, here is the bar magnet, I will this time pull this bar magnet away from this coil. In this case, they will tend to attract each other. Yani coil does not want this time bar magnet to move away. They will tend to attract each other. A force that tends to attract each other is created between the coil and the bar magnet. So then think like this. It's moving away. I move away. This one. Which pole I am moving away? N pole. If N pole must be attracted, so this must be S, because we know that S tends to attract N. If this is S, this is going to be N. But if I move away, S pole facing this one, if S is moving away, this coil does not want S to move away, so then it will tend to attract each other. So S pole is attracted by, and this is going to be N, that is going to be S. In this case, their magnetic fields are going to be in the same direction, both magnetic fields, because we know that if two magnetic fields in the same direction, they will tend to attract each other. Look at that. Magnetic field in here, it's leaving from N entering to S, is it? Look at that. It's entering to S. What is the direction of the induced magnetic field in here? To the left. In here, apply to the left. Both are to the left. They are in the same direction. So if they are in the same direction, they will attract each other. Look at in here. It leaves, we know that magnetic lines are leaving from M pole. It is to the right in here. Look at it here. Also to the right. So they are in the same. So they will tend to attract each other. Yani same directed magnetic fields are tend to attract. Opposite directed magnetic fields tend to repel each other. Okay. This is how we determine the poles of the coil. And which side is the N pole, which one is S pole. And next step. Every magnetic field because of some current in the coil. Now this time we are going to decide what is the direction of the induced current in this coil. Second step. In section 1, chapter 5, section 2, we did opposite. Electric current direction is given in a coil. We found magnetic field direction and the poles. Remember right-hand rule 2. A coil. If an electric current is given to the coil, there are two possible cases. It can go this way and from front to back, or from back to front. There are two possible cases. So according to these cases, we can understand which side is M pole, which one is S pole. If electric current goes from front to back like this, so as you see my thumb shows, the left hand is M pole, right is S pole. But if electric current is coming from back to front, this way, so then right side is M pole, left side is S pole. So we can determine the poles depending on direction of the electric current in the coil. But this time we will do opposite. This time first poles are known, we will find electric current direction. So by using again right-hand rule, 2 we studied in section 2, chapter 5. This is the case. Okay, as you see, a bar magnet is receding. We are pulling it away, direction of the velocity. Look at that. In the case of moving away, what's happening? We know that in the case of moving away, M pole is moving away. We are moving away. This coil and this bar magnet tends to attract each other. To attract it, so N pole is attracted by S pole. This side must be S. If the right end is S, left end is going to be N, not S, of course. It is going to be N. Now we found the poles. After finding the poles, we are going to apply right hand rule 2. So you are going to use your pen for this. So then, which side is ample? Left hand is ample. Thumb must show left hand. Look at my forefinger, which is electric current direction. It goes front to back. Yani, front of the coil goes up, at the back it goes down. Let's draw it. In the front it's up, at the back down. In front up, at the back down. In front up, at the back, from back down. It is from back. Follow the wire without changing direction. What they are going to ask is what is electric current direction on the resistor? As you see, on this resistor it's from right to left. By this way we can find what is the electric current direction. Okay, this is how we find it. Maybe a few examples we can do that, but this is enough. Say that we are going to this time mega approaching. So if we change velocity direction this time, of course, because n is approaching, this is going to be n. If then s, so if poles changes, electric direction becomes opposite. Electric current can be to the right, to left, or left to right, depending on you are going to move them closer or move away from each other. But in fact, what we did in here is based on a rule known as Lenz law. Lenz law is an explanation is a bit complicated compared to this method. This method is much easier than the Lenz law, but Lenz law still can answer questions. First, we have to know what is Lenz law. Lenz law is the rule for finding direction of induced current. As I said in the classroom, this is a ministry question, last year's ministry question. So Lenz law is used to find direction of the induced current. And what does Lenz law states? It's about direction of the induced current. If it's about direction of the induced current, of course, direction of the induced magnetic field. Induced current direction determines induced magnetic field direction. So it's in fact defining magnetic field. Look at that. Magnetic field of the induced current. What is the magnetic field of the induced current? Induced magnetic field. Yani coil's magnetic field. In a coil, yani induced magnetic field in a coil is in a direction. We are defining direction because Lenz law is about what? Direction of induced magnetic field, induced current. The magnetic field of the induced current in a coil is in a direction that, what is direction? How it defines after that? That opposes the change in the applied field. Remember, when I was moving the bar magnet closer, applied field is increasing. It's moving away, it's decreasing. So coil wants to oppose this change. There are two types of changes, I'll say. One of them is increasing applied field, we can make them closer, or decreasing magnetic field, we can make them away. So then, this coil's magnetic field opposes this increasing applied field. How can you oppose an increase? By making another magnetic field in the opposite direction. So induced magnetic field weakens because it is increasing. The coil doesn't want magnetic field to increase. It should weaken that magnetic field. But how can you weaken a vector with another vector? By making the opposite direction. So this induced magnetic field weakens applied field by being in the opposite direction. Now if you make them closer to each other, applied magnetic field direction and induced magnetic field direction is going to be opposite between the region of coil and the bar magnet. Second change which we can make is decreasing applied field. How can we decrease applied field? Pull the bar magnet away from the coil. So coil doesn't want applied field to decrease. So what should coil do? This time supports it. Supports. Yeah, this magnetic field supports the applied magnetic field by being, so we can support a vector by being in the same direction, of course. Yeah, in the case of increasing magnetic applied field, the induced magnetic field weakens by being in opposite direction. In the case of decreasing applied field, moving away a coil or bar magnet, in this case, supports by being in the same direction. But what is the purpose for this? Coil does not want net magnetic field between itself and the bar magnet to decrease or increase. It wants to keep net magnetic field, total magnetic field, unchanged. So, as a result, the total magnetic field strength in a region between the magnet and the coil tends to keep constant. according to energy conservation. So this constant part is another mystery question. So what is the main idea of the Lenz law? Total magnetic field in a region between this coil and the bar magnet must stay unchanged, yani constant. Coil is trying to keep this magnetic field unchanged by supporting or weakening the applied magnetic field. Now I'm going to solve a problem just by applying only this Lenz law, one question. This is the case. As you see, a bar magnet is receiving. You are pulling a bar magnet away from a coil. So, in the case of receiving, and if you pull it away, of course, in this region between the coil and the bar magnet, applied magnetic field should be decreasing because you are pulling it away. So, it's a decreasing applied field of the bar magnet in here. What is the direction of the applied field? Look at in here. So magnetic fields are leaving from and also it's to the left. This magnetic field, which is to the left, is decreasing because we are pulling the bar magnet away. But coil reacts this decrease. It doesn't want net magnetic field or total magnetic field to decrease. That's why it makes its own magnetic field in here by making it in the same direction. Because if it is decreasing, it wants to support it. So then this coil's magnetic field in here is going to be in the same direction. So, supporting induced field of the coil. This red arrow represents direction of the induced magnetic field in here between the region of coil and bar magnet. Then the rest of them we are going to continue drawing them. So, direction of the magnetic field is to the left, induced magnetic field. Continue. Enter the coil. Magnetic field lines are entering the coil. Which pole is this then? Magnetic field enters the S pole. If this is S, this must be N pole. After that, we are going to find right-hand rule for finding direction of the electric current on the coil. So, left hand is N pole, curled forefinger is front to back, in front up, at the back down. So we are going to draw it like this: up and front, down, at the back, up, down, from back down. It becomes from right to left again. Let's apply this Lenz law to another condition, another problem. This time, let's make them approach. Yeah, we are pushing this bar magnet towards the coil. So choose a point between these two, coil and the bar magnet. Here is the point. At this point, what is the direction of the applied magnetic field? So magnetic field is leaving from N pole. It must be to the left. So then I'm going to indicate this is applied field. Applied field. But its applied field is increasing or decreasing? Look at it here, approaching. In the case of approaching, it's increasing. So this is an increase in applied field. Coil reacts as increase. It doesn't want magnetic field to increase. So that's why coil should make its magnetic field to be in the opposite direction of this applied field, and like that. This magnetic field, coil's magnetic field, and induced magnetic field. So this is induced magnetic field. But this induced magnetic field is what? Weakening. Because their directions are opposite. It wants to weaken it. Weakening induced magnetic field. Then, look at the direction of the arrow. It is leaving from the right end. Magnetic field lines are leaving from the which pole? N pole. This is N pole there. If this is N, that is S pole. Then I'm going to choose right hand rule 2 again. Left hand is N pole. My forefinger up at the back, down in front. Yani front to, back to front. We are going to draw it back and front. Back up, front down, back up, front down, back up, front down, back up, front down, go down without changing direction. So as you see, it's going from left to right. And electric current direction of resistors from left to right. This is how we apply the Lenz law to the problems. Only we have to determine first, is this applied magnetic field is decreasing or increasing? If it is increasing, induced field will be opposite. If it is decreasing, induced magnetic field will support it. That's the case for Lenz law. And next title is how much electric current is induced, how much EMF is induced in this coil. By using Faraday's law, we can find this. Lenz law is used to find direction of the induced current only, not how much is the current. We don't have an answer about this. We can know, big or small, but how big, how much, we don't know. So Faraday's law is used to calculate induced EMF. How many volts is the induced EMF? How many ampere is electric current? We can find by Faraday's law. This is Faraday's law. We know induced EMF is, or induced current is because of the change in magnetic flux. Absolutely. Faraday's law must include change in magnetic flux. And delta phi over delta T represents rate of change of magnetic flux. And of course, if there is one loop, it's okay. But if there are more than one loop, 2 loops, 3 loops, you should multiply this delta phi over delta T by number of turns. And also, Lenz law adds this equation a negative sign. Yeah, negative m delta phi over delta T is Lenz law, or negative delta phi over delta T multiplied by n, obviously Faraday's law. So delta phi over delta T is known as time rate of change of magnetic flux. And if they ask me the question that you calculate rate of change of magnetic flux and find delta phi over delta T. They are asking, you are going to know it is in fact magnet of the induced EMF. How much is the magnet of E? Okay. And the problems about Faraday's law is not that far hard. That's why I'm not going to go over with them. I will continue the next title, which is self-induction. Self-induction. In electromagnetic induction, we had a coil and a bar magnet. We make them approaching and moving away, and we make a change in magnetic flux on the coil, and we induce a current in the coil. But in self-induction, we don't have a bar magnet. We are going to have just one coil. Everything will be done by the coil. Applied field done by the coil. Induced field also done by the coil. That's why this title is known as self-induction. Okay. So this is the case. Here is the coil, but if you want to make a coil to produce a magnetic field, you should connect this coil to a battery. Yes, as you see, we connected this coil to a battery with positive and negative terminals. But initially, the switch is open. And if the switch is open, then electric current is going to be 0. I is 0. I is 0. If I is 0, B is 0. Magnetic field of the coil is 0. So magnetic flux through this area is 0. Everything is 0 about this coil at the beginning. But later we are going to close this switch. When the switch is closed, of course, electric current will jump from 0 to a maximum value. Magnetic field in the coil will jump from 0 to a maximum value like this blue magnetic field. And also, magnetic flux through this area will jump from 0 to a maximum value, which is equal to A times B. Yani, when the external electric current is supplied to the circuit by closing the switch, a magnetic field B, which is blue, is produced through the coil. So magnetic flux increases and becomes maximum. So it jumps from a 0 to a maximum. Magnetic flux change from 0 to maximum. Applied field change from 0 to maximum. And coil itself reacts to this increase in magnetic flux, increase in applied magnetic field. So because this applied magnetic field is increasing, coil's reaction is going to be to decrease it. And that's why a coil produces a second magnetic field, which will tend to decrease this blue magnetic field. So this magnetic field selection must be opposite out below. Green one. This green one is self-induced magnetic field. This happens as electric current is jumping from 0 to a maximum value. Because they are in the opposite directions, their electric currents will be also in the opposite directions. For an instant, net electric current is going to be external magnetic field minus induced magnetic field. Also, we saw this title. We talked this when I was talking about 6-3. When in AC, electric current is changing, increasing. So coil is reacting, it's increasing at the beginning. It's making net electric current 0, even though battery generator supplies electric current. Net electric current at the beginning is 0 because of the self-induced current. So this is what self-induction is. Yani increasing applied field, increasing electric current done by coil itself, or self-induced current also done by the coil itself. That's why it's called self-induction. We didn't use another external magnetic field. We used, or it used its own applied magnetic field, but because of a battery provides this external magnetic field. So this is the definition. The creation of an EMF in a coil due to variation, yani change of the current of the coil itself is called self-induction. Self-induction can be observed when you switch on, can close a switch at that moment, or you can switch off. You can also observe it like that. A similar effect is observed in the coil if the external electric current through the coil decreases by time by switching off. When you switch it off, then as soon as you make it off like this, external electric current provided by the battery is decreasing. This blue magnetic field is also decreasing. Magnetic flux through the coil is also decreasing. This time coil is giving reaction to this decrease. And support this magnetic field this time. That's why self-induced magnetic field becomes in the same direction of the external magnetic field. But this happens only for some milliseconds when you switch it off. Yeah, self-induction can be observed when you switch on or off a device at that moment. If you keep it closed for a long time, so there will be no self-induction. Self-induction is about changing electric current. And we can change electric current by two ways. One of them is opening and closing a circuit, on, off, on, off, on, off. Second one is by using a device which is called rheostat, because rheostat also controls the electric current of the circuit. So when you put rheostat in here, you can increase or decrease the electric current. As electric current is increasing and decreasing, you are going to observe self-induction in the coil. Or we are going to observe this in 6-3. If you connect coil to a AC generator. Yes. The AC generator also continues to cause a change in electric current. So you can also observe self-induction when you connect the coil to an AC generator. Okay. Now, we know that if electric current in a coil changes by time, we can make this change by on, off, or we can make change by rheostat. There is going to be induced current, self-induced current. Of course, every induced current is because of a self-induced EMF. So how much is the EMF? Or EMF depends on what? We are going to now talk about this. Self-induced EMF. First, you know that current in a coil directly proportional magnetic affects the magnetic field. Magnetic field affects the magnetic flux. They are all directly proportional. Yani magnetic flux directly proportional to magnetic field. Magnetic field directly proportional to electric current. So if it is so, their changes are also directly proportional. If it is so, rate of change of electric current, rate of change of magnetic field also directly proportional. When we continue this chain, finally we get an equation. This equation tells you that induced EMF is directly proportional to rate of change in electric current multiplied by constant. This constant, which is inserted in this equation, L, is named as coefficient of self-induction. So the constant quantity, this N times constant, is named as coefficient of self-induction. It depends on, next slide we are going to start about this, specification of the coil, yani, length, cross-section area, number of turns, medium, all of them. And its symbol is, as you see, L, and its unit is Henry is H, represented by H, equal to volt times second divided by ampere. How we define this? In this equation, E is equal to negative L delta I over delta T, you are going to transfer this delta I over delta T other side. L is going to be negative E delta I over delta T. After that, you are going to write the units. This is Henry. Henry becomes EMF is volt divided by delta I is ampere. Delta T, 1 over delta T, 1 over second. When you flip it, it goes up in here, it becomes second volt times second divided by ampere is equal to Henry. And more things we can cover. We did it in the lesson. And also I put it in quick revision book that you can see this table. Then as I said, this L depends on specification of the coils. Now we are going to define how can we calculate coefficient of self-induction of a solenoid. We'll talk about this. Okay, two rules we learned until now. One of them is Faraday's law, negative and delta phi over delta. The other one is Henry's law about self-induction, negative and delta phi over delta. They are equal to each other. These two defines the same thing, which is E. Then that's why we make them equal. When we make them equal, we get a very important relationship between magnetic flux and electric current. M times phi is equal to L times I. Even from this equation, we get a unit, remember. Phi is Weber, L is Henry, I is ampere. So this is a Weber is equal to Henry times ampere. And I'm going to calculate coefficient of self-induction of a solenoid. So that's why in this equation I have to write magnetic flux. For a solenoid, magnetic flux is area times magnetic field. The magnetic field of the solenoid is mu I over L. Then these I's will simplify, then I will get the equation. Okay, equation for calculating coefficient of self-induction, mu n squared A over L. In here, n is number of turns. L, small l, length of the solenoid. A, cross-section area. Mu is the medium. Capital L, coefficient of self-induction. Depends on four quantities: medium, number of turns, cross-section area, and length of the conductor. One more thing, when we check this equation, we are going to see that n, because it is squared, has greater effect, higher increase, yani on the change in the magnetic, change in the coefficient of self-induction. Which one leads a higher increase in the coefficient of self-induction of the solenoid? Doubling n or doubling area? Of course, doubling n, because when you double n, because they are squared, it changes by 4, not only 2. Okay, this is what coefficient of self-induction is. Okay, one problem we are going to solve. After that, we are going to finish this title. An air solenoid of length 10 centimeter, which is L. Centimeter is not a SI unit, we convert it to meter. Cross-section area 25 centimeters square, which is area. But centimeter square must be converted to square by multiplying 10 to the power -4, not -2. And 400 turns, which is N. Traversed by a current, electric current I. Now the question. If the current is reversed in during 0.1 second, which is delta T, calculate induced EMF B. This is self-induction. Why self-induction? Because electric current is reversed, means it changes from a positive value to a negative value. That's why this is an initial value. Initial electric current is 4 ampere. Reversed, current is reversed, final is becoming negative 4 ampere. This is the change in electric current. I'm going to use the Henry's law. Yani, E is equal to negative L, delta I over delta T. I have to use this. But to use that, I need to know what is L. First, L must be calculated. We can. We know everything about equation for L of solenoid. Mu n squared A over length of the solenoid. We will not give it air solid 4 pi times 10 to the power negative 7. N is 400 squared. And area is 25 times 10 to the power of negative 4. Divided by length, which is 0.1. I think result is 5 times 10 to the power negative 3, I think.
Yes. No, 5 times 10 to the power negative 5.
Negative 5, yeah. 5 times 10 to the negative 5. 100. Am I right? Negative 3 or negative 5?
Yes, negative 5.
Negative 5. Okay. So then we can now apply. Negative 5 is negative flux. It was negative 3. Negative 3. Yani, it's going to be
It's the
negative
second
3.
solution.
Yes. So negative 3 is the hand, right? Yes. Now we are going to now find E. E is equal to negative delta I. What does delta I mean? I final minus. Yes, we have to write this, otherwise sometimes you are doing mistake. So after that we should insert a number. Negative L is 5 times. This negative, the equation is negative by time, not L is negative. 5 times 10 to the power negative 3. I final is negative 4, which is reversed. I initially is positive 4. Negatives of the equation. 4 divided by 0.1. When we go on with this, we will find the answer as positive 0.4 volt. I think. This was the problem. Yes, I am.
Teacher, there is no given of mu. So how did you?
It will be given, as I said, I forgot. It must be given.
So it has.
Of course, air solenoid, which is mu, must be given 4 pi times 10 to the power of negative 7. Just a time to reach divided by ampere.
Wasn't mu a constant?
Yes, for air it's the same, but from medium to medium it's changing. But this is an air, and in our book there is only mu for air is given. We don't say the other cases.
But it will be given.
Yes, it must be.
We did 2 solutions. That's
Yeah.
why I said the wrong
This
one.
one is the one which is in the question. They ask
This
this
is the
in the exam in this way. That's why better to know this one. Okay. And plus one is eddy current in this section. Remember, when we drop a bar magnet towards that copper block, as bar magnet is approaching the copper block, the magnetic flux of the copper block changed, and this current is induced on the copper block. Circular currents. These circular currents are called eddy current. In fact, it is no different than induced current because it happens on a rigid object. These induced currents are named as eddy currents. Where these eddy currents are used is the ministry question before. They are used in furnaces because eddy current is producing the heat. Maybe the lesson remember we saw how they are cooking. That is. Second one is you can slow down a car by eddy currents. Second one is this. Third one is you can detect metals in airport and underground. So searching the metal on the human body or underground you can also form this. So this is enough. And when this bar magnet is approaching to this copper block, we are going to observe that this bar magnet is not falling like G. It's less than G, which means its kinetic energy is decreasing. Of course, this kinetic energy, which is decreasing kinetic energy, should be converted the electrical energy into copper block. And this electric energy later converted to heat. And heats up the copper block. So this is all about 6.1. We finished 6.1 with this title. We don't have time for next section, which is 6.2. We do next week. Okay? All right. So,